Okay. All right, class. As you know, today is going to be the midterm review. Welcome you guys to ask questions today, but we're going to go through last year's midterm and solve each problem and then take any questions that you guys may have. A couple people left early because they figured they wanted to review the midterm on their own first. If that's the case with you, I encourage you also to do the problems on your own, find out what your weak points are, and then come back and maybe watch this lecture later. One quick announcement. Of course, homework is due. Make sure you turn those in. I'm going to have the solutions up tonight so that you guys can use that to study. If I forget, please send me an email. I'll be on an airplane to Munich, but I may check email on the airplane, so I can do that. Also, Al's going to have a review session tomorrow, so if you didn't get that email, talk to him and find out where it is. Yes?
Are we going to be given things like equations for a cascade of series or an inversion of series?
Yeah. Don't
Feedback.
memorize any equations. Anything that you need will be given to you. So the cover page of the exam is full of equations, and if you find that if you find that you need something that's not on the cover page, you can ask Al and he'll provide it for you. But unless you do something really weird, everything should be on the cover page for you. So what's the equation for IM3? It's given. What's the equation for cascade IP3? It's given. What's the noise figure of a cascade? Actually, I think I forgot to put that one down. Yeah, so noise figure of cascade. But that one's so easy, you guys can remember. Things like that you'll have. Series inversion, all that stuff will be there. Okay? So I'll add that to the cover page since we have to print that out anyway. Okay, any other questions? All right, another announcement. I think the notes are already updated online, but on lecture 9, I made a mistake in the derivation. So in lecture 9, we derived the input IP3 of a cascade. We have two blocks, A and B. And when we did the derivation, we forgot to take the square root. And so, consequently, the right equation is as follows. So this should be squared. So this is A, and this is B. So, and these are all in terms of voltages. So if you go back and look at the notes, you'll notice that the squares now appear. Okay? So thanks to Kevin for pointing that out. Okay? All right, any general questions about the exam material that's going to be covered? Everything up to last lecture is fair game. Some of the more advanced topics, you don't need to know. So what are some of the topics that you don't need to know? So don't worry about correlated noise sources. That was kind of something I lectured on because you guys asked so many questions about it. Wasn't planning on doing it. The other thing is we did this, end tones with a general nonlinearity. It's a cute little derivation, but you don't have to memorize it or anything like that. And I won't ask you guys to tell me what's gain compression due to the 9th order nonlinearity. Okay? So focus on the fundamentals. If all goes well, the midterm should be easier than Al's homeworks. All right. Okay, so let's look at the midterm exam. Okay. So first problem on the midterm, let's zoom in on this one, is basically giving you a new device that maybe you haven't seen before, but it looks really similar to something that you work with every day. It's kind of a dual. Instead of having a transconductance, it has a transresistance. Instead of having input capacitance, it has input inductance. Okay, So this was a piece of cake problem. I mean, it was meant to be, if you know what you're doing, it's a piece of cake. If you kind of memorized formulas and then, you know, for let's say hybrid pi, and you hadn't really thought about where those formulas came from, this problem would be hard. So you can see that it's a piece of cake because it's a unilateral device, right? There's no feedback. So z parameters are trivial to calculate. You can just calculate them by inspection, right? So if I look at this Z11, because it's unilateral, it's just the input impedance of a resistance in series with an inductance. Same thing with Z22. If I basically if I leave the input open, there's no current coming in, so this generator goes away, and Z22 is just this in series with this. And Z21, of course, is just this trans resistance. So it's a very simple calculation for the Z parameters, and in fact, the first part asks you to calculate the maximum gain at 10 gigahertz and give you the equation for maximum gain for a unilateral device, Z21 squared over 4, real part Z11, Z22. There's the expression we calculated for Z11, Z22, here's the trans resistance, and you just plug in. And because these are all frequency independent, this is the gain for all frequencies, so it would be the gain at 10 gigahertz as well. Okay. Any questions about this part of the problem? Yes, Debo.
Like I was wondering, like not exactly this one, but suppose there was a capacitor like that feedback. Like
okay.
I was just a little confused how I could calculate Z12. Like should I leave the input open at that time, and would there be a current through Ln at that time, but no current through Rn?
Okay, so let's look at that problem. So what if there were a feedback capacitor? Let's say like that. So there's two ways to approach the problem. One way is to say, okay, this capacitance is just in parallel, so I know what the Y matrix for a capacitor is. I can convert that to a Z matrix, and then I can just add it. I can add, actually I need to convert this to Y matrix, right? So if I had the Y matrix of this guy, and I know the Y matrix of this, then I just add them to get the total Y matrix, right? But let's say you didn't want to invert the Z matrix to Y. So you want to do it more directly. So, and we want to calculate, let's say, Z12. So I always go back to definitions. I say that V1 is Z11I1 plus Z12I2. So Z12 is V1 over I2, where I1 is equal to 0. That means I leave this guy open. So I1 is equal to 0. Okay? And so I want to calculate V1 when I put in a current I2. Okay? So if I put in a current, because this part of the current doesn't affect, so what I need to do is find this current, right? And all of this current will flow into here and generate V1, right? But part of this current that flows in also activates this generator. So I'm going to write an equation to take that into account. Okay. So I could say that let's see. Let me assume that this is V2. In fact, I think it's easier if I put a voltage source here. So let me, instead of putting a current source, let me put a voltage source and instead measure I2. Okay? So if I put a voltage source here, then this current is very easy to calculate, right? This current coming back. So I could say that In is just V2 divided by 1 over j omega c, the feedback capacitance, plus R, I call this R in, plus j omega Ln. All right? So you're done, right? And then you multiply this by the voltage divider. So V1 is In times Rn plus j omega Ln divided by 1 over j omega c plus Rn plus j omega Ln times V2. Okay? So now I need to find the relationship between V2 and I2, right? So now I can say that I2 is equal to V2, so it's equal to I in plus V2 minus R in I in divided by R out plus J omega L out, right? And I have an expression for I in, so I can basically substitute and find the relationship between V2 and I2. Okay? And I won't do the algebra because I think you can all finish it from here. Okay? Okay, so the next part of the problem is asking us to design a matching network to achieve a match to 50 ohms. Okay? So let me draw the circuit again. So the circuit, again, it's unilateral, so it's really easy. This is 5 ohms. This is 3 nanohenries. And remember, this problem is meant to be a freebie for the most part, so it shouldn't take you too long. Okay, so first thing I notice is that to match this to 50 ohms, I got to get rid of this reactance. So I could just put a capacitance in series. Let's call this C resonance. And the reactance of this guy will cancel out this. So from these terminals, it's a real 5 ohms. Okay? And now I want to increase the input impedance. It doesn't say that you have to meet a specific bandwidth, right? It just says calculate it and then calculate the bandwidth. So basically I can use the simplest matching network that comes to mind. I'll just use an L match. So in an L matching network, I'm going to have an element here and an element here to boost the impedance. And I have a choice between using either an inductor here or a capacitor here. Okay? Now since I already have a cap here, it would be nice if I put another cap here, because then these two caps in series will give me an effective capacitance. And so then I have to use one less element. Or if I use an inductor here, this effectively would cancel out part of that inductance, so I'd have a new inductance. So either way, I can end up with a 2-element match. Okay? And so the first thing you do, of course, is you calculate the Q of the matching network. I know that when I put the series element, if I do a series to parallel transformation, the resistance is going to go from 5 ohms to 5 ohms times 1 plus Q squared. And I want that to equal 50. In other words, the Q is 50 over 5 minus 1 square root, or 10 minus 1 square root is 3. So the quality factor of this matching network is going to be 3. That tells me that this reactance should be 3 times bigger than this, so this should be, let's say, minus J 15 ohms. Okay? And now to finish the problem, I need to find this reactance. The parallel reactance, xp prime, remember, is xs 1 plus q to the minus 2 power. So that will give me 15 times 1 plus 1/9, okay? Or about 10% bigger. So let's say it's about 16.5. And this is going to be inductive. So to finish up the circuit, I have 16.5 inductive. I have the series combination of C resonance and minus 15J. And that's it. That completes the matching network. Okay. And I think I also asked for the bandwidth. So the bandwidth is the center frequency divided by Q. So that's going to be 10 gigahertz divided by 3. Okay. Questions? Yes.
So is the matching Q of the whole matching network equal to the Q of that Q, the 3, which we had calculated initially?
Yeah. So if you want to be more precise, in fact, I was going to just bring this up. What you should do is you should convert this whole thing into a parallel RLC circuit, right? Where this is 50 ohms, this is 16.5 J, right? And this is minus 16.5 J. And then the Q definition is not quite 3, right? So Q is going to be 50 divided by 16.5. Right? So you see it's going to be slightly different. All right, good question. Okay, so the next part of the problem asks you to calculate the IM3. So again, you have this black box, and you connect a load to it, and you're going to put in 2 signal sources and a bias. So this is IQ to bias up the circuit, and then I'm going to put in I1 plus I2 at, let's say, frequency omega 1 and omega 2 to calculate the IM3. Okay. Now you're given some large signal equations. The large signal properties of this device are that the output voltage, Vout, is minus kV. Let me go back here. Minus kV 1 plus In divided by IP. Okay? And so we can write for our particular case that In is IQ plus small signal In divided by IP. And I can basically factor out, I can write this as minus kV 1 plus IQ IP plus In over IP. And let me factor out this term here. Now the assumption is that this is a small signal, so In is much smaller than IP. So this gives me minus kV divided by 1 plus IQ over IP divided by 1 plus In over Ix, where Ix is basically this divided by this. So let me write that down. So Ix is equal to 1 over 1 plus IQ IP times 1 over IP. Sorry. Ix is IP divided by 1 plus IQ over IP. All right? And now I have that the output is minus kV 1 plus IQ over IP times 1 over 1 plus In over Ix. And again, if I assume that this signal is small, I can do a Taylor series expansion of this term, and I get minus kV 1 plus IQ over IP. It's constant terms. 1 minus In squared Ix squared. Sorry, 1 linear term plus In squared Ix squared minus In cubed Ix cubed, and so on. Okay. So now I have a Taylor series expansion output in terms of the input, and I know that IM3 is simply 3/4 A3 over A1 S input squared. This is my A3, this is my A1. Constant doesn't really matter, it gets divided out. So I get 3/4 1 over Ix cubed times Ix signal squared, or 3/4 input signal divided by Ix squared. Okay. And then just to finish this off, I'm given that if I go through and plug in numbers, I find that Ix is 2 milliamps plus 3/4 of a milliamp, and my input is 100 microamps. So this gives me minus 60 dBc. All right. This is dB carrier, so it's a ratio of the input signal to the carrier, the fundamental. All right. So again, this was a problem that was fairly simple. The idea was to get you guys to, or to get last year students to do a calculation on something they hadn't seen before, but calculations were simple enough that they could just do it without detailed math. Okay. And I'm assuming that everybody knows how to do a Taylor series expansion on 1 over 1 plus x. Okay. Okay, any questions? All right, then the next part asks you to do the calculation when you have this RF. And you're even told that this is a feedback resistor, so if the word feedback wasn't ringing in your head, there's something wrong with you. If you're clever, though, you would actually make sure that this is negative feedback, right? So you should first of all verify that this is negative feedback. Okay? And if you verify that the feedback is negative, then you can use the formulas that we derived in class. So all you need to know is the loop gain. So to find the loop gain, you need the feedback factor, right, and the forward gain. So you're given in the problem that RF is much bigger than Rin. In other words, the input impedance is very low. That means that the feedback current, IF, is approximately V out divided by RF. Okay? Because V in practically doesn't move at all. It's very low impedance. So that means that F is simply 1 over RF. Okay? Any questions about that? Okay, well, what's the forward gain? Well, the forward gain is basically we break the amplifier and include the loading. We apply an input signal, let's say IX, and we find the output voltage. Okay. Now, because the input impedance is very low, almost all the current is going to flow into our amplifier, right? In fact, you're told that RF is much bigger than the input. So that means that all of In goes into the amplifier, and the output voltage, therefore, is just Rm times In, which is Ix. Which means the forward gain of the amplifier is simply Rm. Any questions? Okay. And that means that the loop gain, which is the forward gain times the feedback factor, is simply Rm over Rf. Okay. And you're told that Rf is 25 ohms, and we need to calculate Rm. So if you look at the equations, if you linearize the equation, or basically based on the previous problem, Rm is the linear term in that Taylor series expansion. So if you plug in numerical values, you get that Rm is about 60 ohms. Okay? And so then your loop gain is 60 ohms divided by 25 ohms. And so this is about 2.4. And so finally, to calculate HD2, HD2 is nice because it's the HD2 without feedback divided by 1 plus the loop gain. Okay? And we have the loop gain, we have everything. Again, I won't bore you guys with the algebra. We just do a little bit of substitution here. So HD2, which we calculate from the expressions on the previous page. By the way, I'm going to post these solutions online tonight. So you can spend some more time. And if you plug in the numbers, you get an HD2 of minus 21 dBc. Okay. Questions? Yes.
So, like, by calculating the forward gate, just instead of figuring out that RM, could we just, what you later said, just look at the expansion that we had done in the last part and see the coefficient of the linear term?
No, because that doesn't include the loading. Now, in this case, the loading didn't affect the answer, right? But it could have. To keep the problem simple, I made it so that loading didn't really come into play.
You have to assume that our out is completely lower than C2C.
That's also another assumption you have to make. So so as far as the output voltage goes, right? The output voltage has a voltage divider effect because there's a inductor and L in series here. And so we've neglected that. But if you want to do a more careful calculation, you could easily include that too.
We couldn't have made an expansion around IQ equals 2 milliamps. Then we would have gotten A1, A2, and A3.
That's what we did for part C.
It doesn't work for part D.
No, because in part D there's feedback, right? Now there's two ways to solve the problem with feedback. One is you could write all your equations, basically have a nonlinear equation that includes the effects of the feedback, and then do a Taylor series expansion. That's kind of the long way. The short way is to recognize the feedback and try to use the results of the previous problem. Okay. Yes.
In one of the homeworks, we actually were allowed to ignore loading due to the feedback. And when can we do that?
Now on the midterm, I mean, in real life, you can do it when you can, right? When it makes sense. On the midterm, you can kind of assume that the problem has been designed so that you can solve it relatively quickly. So if you find yourself doing 2 pages of calculations, you're probably going down the wrong path. Okay. All right. Okay. So the next problem. The next problem is a 2-stage amplifier. You guys will recognize that it's a common gate amplifier, right? M2 is a common gate. The input's at the source, the output's at the drain. The gate is grounded by this large capacitor. And the second stage is simply a source follower. So it's a 2-stage amplifier, and you're told that this resistance RB is much bigger than 1/GM of this device, and our drain is much smaller than the output resistance. Now, so these are 2 big hints. It's saying when you do your analysis, make some nice simplifying assumptions. Forget about RO of this transistor, right? And the RO is actually going to be even larger because of RB, right? So it's a very good assumption to neglect RO of M2 and just assume that RD loads the drain. Okay? So the first thing you're asked to do is to calculate the bandwidth of the amplifier under the conditions that it's driven with an input and output match, right? So let's redraw the circuit. I drive this with a source which is also 1/GM because you're told that it's matched. And I also load it with 1/GM. Okay? And then you're told to calculate the bandwidth of the amplifier. Now, along the lines of the comment I just made, you're not really asked to do a detailed analysis of this and find all the poles and zeros. That would just take too much time. So what you should do is you should just identify the signal path and identify the highest impedance node and just assume that that's your dominant pole. Okay? So in this circuit, of course, the input is low impedance because the source is low impedance and the input is low impedance. The output is low impedance. And so you're just left with one node. It's pretty simple. This is the dominant node. Okay? So I can now find the total capacitance and total resistance at this node. So what's the total capacitance? Well, I should include C mu of this guy. So I should also include C mu of this guy. Let's call this M2, this M3. I also have drain to bulk here. There's no Miller effect that I have to worry about because both of these transistors are not hooked up in that way. And there's CGS of this guy, but it has series feedback. So the CGS gets reduced by the effect of the series feedback. So let me just sum up. Drain to bulk of 2, that's this guy, plus C mu of 2, plus C mu of 3, that's this guy here, plus CGS of 3 divided by 1 plus GM3 RL. Okay. But you're told that this is matched. That means that GM3 RL is equal to 1 because it's output matched. So I get a factor of 2 reduction in the capacitance. And the total resistance at this node is just R drain, as we discussed. So the total time constant is just RD times C total. And you're done. You assume that the bandwidth is 1 over 2 pi times T. Okay. Questions? Comments? Good. All right. So the next problem, it's surprising how many people miss this, says to calculate GT max and just explain your assumptions, right? So a few pages back, we have a formula for GT max for a unilateral device. The question is this unilateral? Okay. So if I look at this amplifier, and I make the assumption that it's unilateral, so I just say assume unilateral, then the answer becomes very simple. And there's a hint that it should be very simple because look how much space you're given. Right? So if you have to calculate y parameters for y12, forget it. You're going down the wrong path. Okay, so what's y11 approximately? Well, y11 at moderate frequencies is just basically GM2. Right, this is M2, this is M3. Okay? And likewise, y22 at moderate frequencies is just this in parallel with this, but you're told that this is much less than this, so it's also roughly GM3. Okay? How about y21? y21 is the drain current, let's say ID3, or let me just say it's I2 over V1 when I short the output, right? So if I short the output, all the drain current from M3 flows to the output. So I could just say I drain 3 over V1. Okay. And in the spirit of the simple approximation, V1 is just GM2 of the device times our drain. I'm sorry, I should call this, let me not call this V1, let me call this Vx. So Vx is simply V1 times GM2 times RD, right, common gain amplifier. And so then I just need to take into account the GM of transistor 3. So GM3 is little gm3 divided by 1 plus gm. Well, I've shorted the output, so the effect of the degeneration goes away, times 0, so it's just gm of 3. So that means that y21 is simply gm of 2, gm of 3 times rd. Okay? Yes? Because we short the output to calculate y21. Okay, can you repeat your question?
All the Y components, Y11, Y2, don't have something you can count. I mean, it doesn't matter whether it's zeroing on the amplifier or not because you don't involve the R feedback at all.
No, it does matter. Let me explain. Let's say we're calculating z parameters. If we're calculating z parameters, this degeneration would matter, right? It's just when we basically calculate y parameters, we short the output, and it makes the calculation much simpler. But I don't think I got your question, actually. All right, good. Okay, so now I have all the y parameters, and based on the formula, GT max, it's stable because it's unilateral, so I can just use this equation. So this gives me GM2, GM3, R drain squared divided by 4 GM2, GM3, or basically GM2, GM3, R drain divided by 4. R drain squared divided by 4. Okay? And if we assume that this is actually matched so that the GMs are equal to the source impedance, I get 1/4 R drain over RS squared. Okay, any questions? Okay, so the next part is noise. You're asked to calculate the noise figure. So we want to calculate the noise figure under the following condition. Source resistance is RS. You have a matched load equal to RS, and the amp is designed for input and output match. Okay? So that tells me that if it's designed for an input matched, GM2 is equal to 1 over RS, and since it's designed for an output match, that tells me that GM3 is also equal to 1 over RL, which is also 1 over RS. Okay? Now, the situation for the students last year was slightly different because they had a problem where they had to calculate the noise of a common gate amplifier. Okay? So those students, again, this is a test. You don't have that much time. It's probably not good to do detailed calculations. So what I was hoping students would do is basically take the noise of a common gate and cascade it with the noise of a follower. So the expectation I had was that they would basically replace this problem with an equivalent problem, the noise equivalent, just driving a common source loaded with RS. So all they had to do was really find the additional noise added by the second transistor, and they could add it to the noise of the overall to get the total noise. Okay? So really the problem narrowed down to finding the noise of a follower. Okay? Now, since we haven't done the noise of a common gate, I'm going to take some time and do that calculation with you. In fact, we're going to do both the common gate amplifier and then the source follower. And I think this is good practice for the exam. So we'll take our time and really do an extended version of this problem. Okay. Any questions? All right. So let's first of all do the common gate. And I'm going to just do the problem fairly, I'm not going to make too many simplifying assumptions. I'm just going to do the problem fairly completely. So I'll find the total output current where I have drain noise. And another important assumption is that you're told to neglect gate noise. Okay? So that makes the problem a lot easier too. That means that for my FET, the only noise source is ID. Okay? And I have RS and IS. So this is the equivalent circuit that I have to solve. In other words, this is the equivalent circuit for Vs Rs I out. And you can see that the problem is not quite trivial because we have this issue again that we see a lot now. We solved this problem already because we looked at the noise of a cascode amplifier, and so we found the effect of the drain noise to the output. So if you remember that result, it's quite nice. You can just directly apply it. You don't have to do any calculations. But for the sake of completeness, we're going to rederive this result. Okay. All right. So the idea is, in this problem, we're going to work with voltage signals, and then at the end, hopefully we're going to have a sum of independent variables, and so that we can find the RMS value by just summing RMS values. Okay. So what we're really after is I out, which we notice is the sum of GM V pi drain noise. Okay. At this point, we're treating this noise as a deterministic signal. Okay, so let me just write KCL at this node here. If I write KCL at this node, I have several terms. This is basically minus V pi. So I have minus V pi j omega CGS. That's the current going in this direction out of that cap. I have IS. Okay. I have the current going through RS, which is V pi GS. And then I have the current minus GM V pi and minus ID. Okay, I arbitrarily pick a phase for ID and IS. And remember that it doesn't really matter what phase you pick because these are noise, but just be consistent throughout your calculation. Okay? So I'm picking a direction for these two guys. And if I basically collect terms here, I have V pi j omega CGS plus GS plus GM is IS minus ID. And so now I have that the total output noise is the drain current, this current, plus GM V pi, plus GM, and V pi from here I have IS minus ID divided by GM plus GS plus J omega CGS. Okay? And again, I can collect terms here. I can sum my GM terms for the first term in terms of IS, and for my second term, you can see that I get 1 minus this expression. So if I carry the denominator, 1 I can write as this over itself, and when I subtract it, you can see that the GM term goes away. So this is going to be just J omega CGS plus GS divided by GM plus GS plus J omega CGS times ID. Okay? And basically, I can make the argument that these two are independent noise sources, right? IS and I drain are completely independent. And so then I can easily find, let's call this alpha and this beta. So then I can say that the total output noise is alpha squared IS squared plus beta squared I drain squared. Okay? In other words, the noise figure is 1 plus beta squared over alpha squared, drain noise over source noise. Okay? And because alpha and beta have a common denominator, it's very easy to take the ratio. The ratio is simply this thing, magnitude squared, divided by the magnitude of this squared. So beta over alpha squared is GS squared plus omega squared CGS squared divided by GM squared. Okay, any questions up to here?
Why did we neglect that RL load of the gate?
We'll bring it back later. Yeah, that's a good question. We're just going to find the total current and then we can apply it more generally. Okay. Any other questions? Okay, so if I come back here, I have F is 1 plus GS squared omega squared CGS squared GM squared. I drain is gamma over alpha GM, and this is GS. Okay, and you can see this cancels here. And at low frequencies, I get 1 plus, this GS cancels out with that one, GS over GM gamma over alpha. Or 1 plus 1 over GM RS gamma over alpha. Okay, so this is a noise figure of a, common gate amplifier at low frequencies. And you can go back here and see what it means to be at low frequencies. It means that basically at a frequency where the source conductance is much larger than omega CGS. That means that GS is much bigger than omega CGS. Okay. And if we have an input match, so for a matched case, GMRS is identically equal to 1, which means that my noise figure is actually 1 plus gamma over alpha, which is in fact pretty bad, right? And we talked about this when we talked about common gate amplifiers. This is one of the reasons why we don't use common gates very often as low noise amplifiers, because this noise is actually pretty large. This factor might be on the order of 2. So we get a noise factor of 3. Now, there's one interesting thing a couple interesting things that come out of this calculation. If I come back here and I notice basically a pattern that the drain noise is basically at low frequencies attenuated by this factor 1 plus GMRS, right? So at low frequencies, this is 1 over 1 plus GMRS. And at low frequencies, this term is GM over 1 plus GMRS. It's GMRS, 1 plus GMRS. Okay, which is approximately 1 as the loop gain becomes large, right? So as the loop gain becomes large, all the source makes it to the output, but the drain current gets rejected. Okay. Excuse me. And this is essentially the same conclusion we reached when we analyzed a cascode amplifier. It's really the same thing. Well, what about the gate noise? Now, in this particular problem, you've been asked to neglect the gate noise, but we can include it. So let's try to include it. The nice thing about noise calculations is that you can always start off really modest. Neglect all the noises except the ones you think are important, and then incrementally add noise sources. And because of superposition, it's pretty easy to do that. You just add another noise source. You add a new term to your output noise voltage, and so then you get an incremental noise figure increase due to that. So remember, in lecture we derived that the noise was at least 1 plus gamma over alpha under the matched cases, and we put the greater than because we know that there's other noise sources that we've neglected. Okay, so what about gate noise? So if I come back to my circuit and only include my gate noise, then this is quite simple, right? Because this is just a degenerated amplifier. So I don't have to write any equations. I just say that the output is just GM times VG, where GM is the feedback degenerated GM of the device. And so if I say that the output noise just due to RG, is is going to be GM 1 plus GM RS. I shouldn't look at my notes. Okay, so the output we found on the previous page due to the source is actually GM RS 1 plus GM RS times IS, right? Then the fractional noise figure is this noise divided by this noise. So it's GM squared V gate squared. Denominator is the same, it goes away, divided by GM squared RS squared IS. Okay? Let me make sure everybody understands that. Questions?
Is this at low frequency?
Yeah, we're still assuming that we're at moderate frequencies where we've obviously neglected the effects of CGS. Okay. All right, well this simplifies. It's actually kind of interesting to finish it off. So the GMs cancel out, so we get V gate squared. So that just gives me RG, RS squared, and then IS just gives me GS, so this cancels out. So I just get a ratio of RG over RS, which is pretty much what we found for the common source amplifier as well. So if I break RG into two components, the channel component, which is completely independent from the drain component, and the poly component, and then I observe that RS is basically also 1 over GM for this particular amplifier, then my total noise figure is 1 plus gamma over alpha, that's what we found on the previous page, plus the first term, which is RG over RS, just gives us 1/5, plus the last term is R poly times GM, or R poly over RS if you like. Okay? And this is the delta F that we just calculated. Yes?
I don't understand how we came with the delta F.
Okay, let's review how we got delta F. All right, to get delta F, first I calculated this additional noise to the output. By superposition, I set all other noise sources to 0, just find the noise from this gate to the output, right? Then I go back to my previous page where I calculate the output due to the source, right? So this equation tells me that the source makes it to the output with this transfer function. Okay? So all I did was I copied that again. So I wrote that the output due to RS is equal to this. This, if you like, is the output due to VG. Okay? And by definition, the noise figure is the total noise at the output divided the noise just due to RS. So the total noise will include this term here as a plus this noise divided by this, which is the noise just due to RS. Okay? Other questions? All right. So if you guys have good memory, or if you've done lots and lots of homework, then you could easily do this calculation by just observing. Again, this is the low frequency calculation, so this is the drain noise. Again, this is I out. This is GM V pi. This is RS. And this is IS. So if you had to do this calculation very quickly, you know, this is kind of what I was hoping was students had done this in homework and, you know, spent 3-4 pages of algebra, and then at the end of the day they said, there's a very simple lesson to be learned here. And that lesson is that the drain noise at low frequencies gets rejected by 1 plus GMRS. Okay? And the source noise has almost the same transfer function, almost the transfer function of 1, right? And that's it. So then from here they would just write F is 1 plus the ratio of this over this, which gives them basically, I won't do it all over again, 1 over 1 plus gamma over alpha. Okay. Well, how about that second stage? Okay. Second stage is again very simple, very similar. I shouldn't say simple. So second stage is the follower. Okay. So for the follower, I have some source impedance, R drain, and I go into a load of Rs. Okay. So let me draw an equivalent circuit. Let me call this V equivalent. This is the equivalent noise of the first stage. And notice that this is the output now. And what I'm going to do is, again, use superposition, ignore the noise coming in, because the transfer function to the output is quite trivial, right? It's just a follower. And just focus on this drain noise, which maybe is not as trivial. Okay? So what I'm interested in knowing is how this drain noise generates an output voltage noise. And again, it's the same story. This drain noise generates a voltage here, which generates a current here, which subtracts out part of that current. And so I have to be a little bit more careful when I do the calculation. Okay? Well, it's almost the same exact calculation because, again, the current coming into, let's say, here is this sum current, which we've seen many times before. It's GMV pi plus I drain. This current times basically the current divider, Rs plus R drain plus J omega CGS, is the current flowing through here. This 1 over, thank you, this times 1 over J omega CGS generates V pi, right? And so this is equal to minus V pi. Okay. So let me multiply the numerator and denominator of this equation by J omega CGS. Which nicely cancels out here. Okay. Any questions up to here?
So you're doing this only for the drain noise, one source at a time, not taking the noise due to Rs.
Yeah. So yeah, we'll come back to the noise due to Rs. Okay, so let's finish this off. So here, this equation, let me multiply this denominator on the right-hand side. So I have basically Gm V pi Rs plus 1 plus Rs plus Rd J omega CGS times V pi is equal to the right-hand side, which is just going to be minus ID times Rs. Okay? And again, let's just keep the calculation simple. Let's go to low frequencies. Okay? So at low frequencies, I have GMV pi Rs. This term is negligible, so I get plus V pi is equal to minus ID Rs. And so GMV pi is minus ID Rs times GM, 1 plus GM Rs. Okay? Same exact expression that we got before, because it's the same thing, exactly the same problem. So now I sum currents, and you can see that ID gets canceled out partially. And we get this suppression factor. Okay. So the lesson is that, again, if you'd done a lot of homework problems, you wouldn't have to do all these calculations. You would just say, oh, I know that the sum of this current and this current is the drain current divided by 1 plus GMRS. Right? I'm done. I don't need to redo that calculation again. Okay. And so then the output due to our this drain noise is basically 1 plus GMRS I drain times RS, and I just multiply it by RS because our drain is a high impedance, right? Much bigger than RS if I want to get power gain. So this impedance is going to be larger than this impedance. So almost all of this current will flow into RS. Okay. That seem reasonable to everybody? Good. Okay. And basically, so if I want, so this is the noise due to second stage, so I could call this ID3, I guess I was calling it. And now I can go and solve the more complicated problem. Now let me just say a few words about the noise about RS. It depends on who you talk to, right? But the noise of the load is sometimes part of the noise figure, sometimes it's not. You should just be clear. A lot of times, and I think Cadence does this, is if you calculate noise figure, it will not include the noise of the port that's loading it. So if I have basically this large resistor here, which we're going to ignore its noise, and then we have this port, we're not going to include the noise of this port in the noise figure calculation. Okay? Now, the reason is that this is going to drive another stage, and we don't necessarily know its impedance, and we don't know its equivalent noise. For instance, the next stage, let's say the next stage is a degenerated device like that. Well, that device has a 50 ohm input impedance, let's say, but it doesn't generate noise. So it wouldn't be fair to include this noise, right? So that's one of the reasons for keeping it separately. Okay, so let's come back to our problem and finish it off, finally. This problem, I think, if you want to do it right, is too long. So what I was really looking for on the midterm was a very quick and dirty approximation, which I'll tell you guys what it would be if I had to make it. Somebody held a gun to my head and said, what's the noise? You've got 10 seconds. I would say it's the noise of the common gate. Second stage is not going to contribute noise. So I would say it's 1 plus gamma over alpha. Okay. And the reason I would say that, why is that reasonable? Anybody want to take a stab at it?
Because the current that's providing current gain, second stage. So the current to the output doesn't get to the input that much.
Yeah, that's a good way to look at it. The very simplistic way to look at it is that the noise sources here, basically, the gain here is very low, right? The voltage gain. So if I look at the voltage noise here to the output, it's already gone through some gain through this transistor, whereas the output noise here has no gain. So this, if you're thinking about it in terms of cascade, it's not really a cascade, it's very crude. The noise figure of the first stage is going to dominate the overall noise. And I know the noise of the second stage is not that large, partly because of this degeneration, right? In fact, I know that this noise will contribute to the output by a factor of 1/4, because the GM of this transistor is equal to this RS. So I get a 1/4 factor. Okay. So let me calculate V1, the noise over here, based on everything I've learned. So V1 is basically, if this is a high impedance, is just going to be the noise of RD. So VRD, that's simple. And then it's going to be the noise of this guy divided by 4, right? Because I have 1 over 1 plus GMRS. GMRS is 1. 1 plus 1 is 2. 2 squared is 4. Times RD squared. That flows into that point there. The noise of IS is basically also going to be 1/4 RD squared, because it's GMRS squared divided by 1 plus GMRS squared. And again, I have a match. And basically, now I can say that the output noise, this is V out, is V1 squared times the voltage gain of this stage, which is basically GMRS 1 plus GMRS squared, plus the noise of this device, M3, which we also figured out gets rejected by a factor of 4. Okay, so this is also a factor of 4, 1/4. So again, coming out here, this is the total output noise is V1 squared over 4 plus I drain 3 squared RS squared over 4. And if I just substitute for V1, I found that V1 is VRD plus I drain squared R drain squared over 4 plus IS squared R drain squared over 4 plus I drain 3 squared RS squared over 4. Okay. So that's the total output noise. This is the noise due to the source only. So now by inspection, I can write that the noise figure is 1, right? That's this term divided by itself. When I divide this term by this term, I get 4RD divided by RD squared IS squared. IS is just GS. The noise of this guy, I just get RD squared gamma over alpha GM divided by GS. Okay. And finally, this term here, if I divide this term by this term, I get 4 times RS squared gamma over alpha GM of 3. All the GMs are equal, so I don't even have to worry. Divided by this term, which is GS RD squared. Okay. Now GM is equal to GS. Let me be careful here. What did I do wrong? This is this term. This is this term. So that gives me 4RD RD squared GS. That looks right. This term is... Oh, RD cancels out. They both have RD. Okay. And then here, that looks right. Yeah, I think that looks right now. So let me simplify this a little bit. So F is 1 plus 4 RS over RD. That's this term here. Plus GM is equal to GS, so I get gamma over alpha. Plus this last term again, GM is equal to GS. So I get 4 RS over RD squared gamma over alpha. Okay. And if RD is much bigger than RS, you can see that effectively the noise is the same as the noise of the common gate. So the second stage doesn't hurt the noise figure too much. Yes?
Is the last term 4 RS over RD squared gamma over alpha mainly from the second stage?
This is from the last stage, right? This term is only there because of the last stage. Yeah. So you can see that the last stage, if RS is smaller than RD, generates much less noise because of the square factor. So if this is 1/10, this is 1/100th. Okay, we have another 10 minutes. Let's finish up the last problem. Any other questions about noise? Yes.
So for any general cascading, do we multiply the output voltage noise of the first stage by the voltage gain of the second stage and then just add the noise of the second stage?
You could do it that way, yeah. You have to be a little careful though. So it's, you know, it's a voltage gain squared. You have to make sure that the voltage gain is the appropriate thing to use. In this case, the input impedance is very high, right? So there's no loading effect, so you can just use the voltage gain. If there's some loading effects, you have to take that into account. All right. Okay, so the last problem is a cascade, speaking of which, but it's more of a system design. You're given basically two amplifiers in cascade. The first amplifier has a gain of 30 dB and noise figure of 1.7 dB. The second amplifier, not necessarily the second in the cascade, but you just have two amplifiers, has a gain of 20 dB and a noise figure of 1.3 dB. And you're kind of asked here to determine the optimal ordering of the amplifiers. In other words, which is better, to put this amplifier first, which has a lower noise figure but less gain, or put this amplifier first, which has basically a worse noise figure but more gain, so it can reject the noise of the second stage better. Okay? So what's the optimal ordering? Okay. So this is pretty easy. We know the noise figure of a cascade. Let's assume I have 1 and then 2 is just F1 plus F2 minus 1 over G1. And basically I need to convert, this is just a gain of 100, right? This is a gain of 1,000. This noise figure works out to be 1.349 if I convert it from dB to linear scale. This is 1.479. So if I plug in here, I get 1.349. This actually is, no, 1.479 plus 1.349 divided by the gain of 1,000. And if you work this out, this gives us a noise figure of 1.479. Okay. Gain is so large that it really doesn't matter, right, that you cascade. Well, what about if we take F21? Well, F21 is F2 plus F1 minus 1 over G2. Now, don't get confused here, right? This is not the general formula. But if we plug in numbers, F2 is 1.349 plus F1 minus 1 is 0.479. Now the gain is only 100, so I get 1.354. So I get a noise that's slightly larger than it was before, but still smaller than the other amplifier. So that means that order 2-1 is better. That's it. That's the answer to the problem. Very simple. Okay. Now this seems like a very simple problem, but if you think about this for a while, you actually come up with a really interesting noise metric. So the noise figure as a noise metric has some problems, right? One of the problems is, it's a classic question, what's the noise figure of an ideal wire? It's 0 dB, right? Ideal wire has no loss. But it also has no gain. So it's not really that useful. So somehow it would be nice if we had a noise metric that took gain into consideration. Okay? And it turns out that if I calculate M, which is called the noise measure, which is defined as the gain times the noise figure minus 1 divided by the gain minus 1, then this noise measure is a better way to characterize a device than the noise figure alone. So the noise measure, in fact, if I calculate the noise measure of amplifier 1, I get 1.479, and the noise measure of, which is more or less the noise figure because it's a high gain device, and the noise measure of the amplifier 2, I get 1.353, and you can see that the device with the lowest noise measure is actually the best device. And did I do this in the notes? Maybe not. Basically, you might ask, well, where does this noise measure come from? And I'll let you guys do this at home. If you take an amplifier and cascade it with itself, in fact, you form the infinite cascade. And calculate the noise figure of this infinite cascade, you get the noise measure. So noise measure is also, it's a pretty nice thing. There's lots of deep noise books and papers written about it. But for our purposes, we're done with it. Let's move on. Okay. All right, so the second problem asks us to find basically the minimum detectable signal for this cascade in order to maintain a 10 dB noise figure. Okay? And you're given that the bandwidth is 1 megahertz. All right. Okay, so by definition, we want the signal noise ratio at the output to be 10 dB, or a factor of 10, and let's do dB, and that's the SNR at the input minus F, right? Because the system always degrades the noise figure. So all we have to do here is solve for the SNR at the input is 10 dB plus F, and we set the SNR at the input, which is equal to P min, the minimum signal that we can detect, minus the noise at the source. Okay? And so P min is 10 dB plus F plus the noise of the source. Okay? And so I have 10 dB here. What's F in dB? I think it's around 1.3 dB. I don't have it calculated. And what's NS? Well, NS is basically minus 174 dBm per root hertz. So all I need to do is add the bandwidth, and the bandwidth here is 1 megahertz, so that gives me 60 dB. Okay? So this is 60, 70, so this is minus 104 plus 103, so it's about minus 103 dBm. Questions?
So, like, instead of doing KTB, if I had done 4 KT RS into B, I get a different answer.
You shouldn't. Are you sure you did dBm? Divide by a milliwatt. Yes, Kevin?
I guess this is a general question. So when we have a condition system, what part of the scheme is our coding or modulation scheme?
The 10 dB part. So this is, you either do some calculations or you do some simulations to determine that to get a bit error rate of 10 to the minus 3, you need 10 dB SNR. Okay. All right, let's wrap it up with the last part. So the last problem says we want to work with a signal as large as minus 10 dBm. So this is the largest signal as opposed to the smallest signal that we did in the last part. So what's the IIP3 in order to maintain a signal to distortion ratio bigger than 10? Okay. Now, one way to approach this problem is to say, at the IIP power, the signal to distortion ratio is 0 dB, right? So if I back off 20 dB from the IIP3 point, then my IM3 improves only by 10 dB, right? So that's it. I want 10 dB, so I back off 20 dB from IP3 point. Is that right? Yeah, because it improves 2 to 1. Thank you, not the other way around. So if I back off 5 dB from the IIP3 point, remember the IM3 improves, so IM3 slope is 2 to 1. So if I basically plot, this is my IM3, this is a slope of 1, this is a slope of 2. So if I back off, thank you, 5 dB from this extrapolated point, this will give me 10 dB. And I want that point to be minus 10 dBm. So that means that my extrapolated IP3 point should be minus 10 dBm plus 5 dB, or minus 5 dBm. And that's the answer.
I have a doubt here, like when my signal is minus 10 dBm, my distortion is minus 20 dBm.
IM3, for this particular example,
Yeah.
remember if I back off 10 dB, my IM3 improves by 20 dB.
Yeah, so looking at the other way, when my signal is minus 10 dBm,
Mhm.
maintain a signal to distortion ratio of 10 dB, my distortion should be minus 20 dBm.
Mhm.
So if I now increase my signal by 10 dBm, my distortion will increase by 20 dBm.
Mhm.
So I reach the equal point.
Mhm.
So where does this spike come from?
Okay, so if you're talking about distortion, it's cube, right? Distortion alone. When I take the ratio of distortion to signal, it becomes square. So if you think about distortion, it's cube. Okay. All right. Make sure you turn in the homework if you haven't done so already, and good luck on the exam.